righty, there we go. Let's do a percent error, okay, a propagated error problem. Let's do, I don't know, we can do whatever you like. We could do surface area of a cylinder.
I think there was one on the homework.
Go ahead, what was it?
Well, I don't think there was one. I'm saying.
Yeah, there was.
There was.
Should have been somewhere. I
Oh, maybe it was.
don't know. Well, let's do one. It's on the test. I'll tell you that right now. So let's do one. Surface area, pi r h, 2 pi r h. Okay, 2 pi r h. Surface area. It's a lateral surface area of a right circular cylinder. And let's suppose the r has an error of plus or minus 1%. And let's suppose the h has an error of plus or minus 2%. Okay. Those are the errors in the measurements of r and h. And what we want to do is calculate the propagated error. The error that's propagated through the calculated surface area of this right circular cylinder. And the way to do that is first find the total differential of S. Okay? The total differential of S, ds, is equal to partial of S with respect to R, dr, plus partial of S with respect to H, dH. That's the total differential of S. And it makes sense, because this is how fast it's changing with respect to R times the change in R. Okay? How fast it's changing with respect to R and then the change in R. This is how fast it's changing with respect to H times the change in H. So the change in S is going to come from two sources, R and H. This is the change in S that comes from the change in R. This is the change in S that comes from the change in H. And that makes sense. It's made up of two components. How much change is there? Well, you got the change from R, you get the change from H. Okay, add them up. That's what you got here. So, ds, that's the error, okay, is equal to the partial of S with respect to R, 2 pi H, dr. dr is the error in measuring R. It's the change in R, and that's a plus or minus 1% of R. Partial of S with respect to H is 2 pi R. dH is a plus or minus 2% of H. And what we have here is a 2 pi RH common factor that can be taken out. Okay. And you end up with a plus or minus 0.01 plus a plus or minus 0.02. Okay, I've taken out a 2 pi RH out of each of these. That's 2 pi RH times a plus or minus 0.03. Okay. But what is 2 pi RH? It's S. Okay? So here's what we have. The relative error is equal to this plus or minus 0.03 S divided by S to get plus or minus 0.03. The percent relative error, which is the way this is always reported, is to change this to a percent multiplied by 100%. And you drop the plus or minus. It's understood to be plus or minus. Percent relative error would be 3%. That's understood to mean it's plus 3% or minus 3% of the calculated surface area. So it's a 3% error. Propagated error is going to be the sum of the two errors. That's the kind of problem you're going to see. Yeah,
DR and DH are the percentages, right?
Yes. Well, DR and DH are the amounts of error. Yeah, the percentage, plus or minus 1% or 2% or 3% error, yes. Times the radius or height or whatever it happens to be. Yep. What do you think, Dave?
That's the relative error.
That's percent relative error. That's what you're going to be asked. Dylan.
So are you kind of like integrating those 2% to add in the H and R? Like the plus or minus 0.01 R, and then the plus or minus 0.02 H?
This, I'm replacing dr with its error and the dh with its error. These numbers are coming from here.
Right, but the R and H, the coefficients or whatever, yeah, those are coming from integrating?
No.
No?
No. They're from taking the partial derivative of the original with respect to...
I think he's saying the R is in the .01.
Yeah.
Where are you getting the R from?
Are you just like...
Yeah, I was wondering that.
Oh, the R here?
Yeah.
Oh, all right. What does a 1% error mean? It means 1% of R.
Okay.
I probably could have written it, and I probably should have written it there. Oh, H here.
Okay.
Okay. Yeah. That would make more sense, perhaps. Okay. Good call. Thanks, Kyle. All right. Anything else you guys want to do? Any other questions?
Could you do some examples of tangents and normals?
Sure. What you're going to have is problem where I give you a surface, and I'm going to ask you to find a normal to the surface at a given point, and the equation of the tangent plane to the surface at a given point. So let's do something like that. Let's do a surface. How about z equals xy? And let's take a point, P, 1, 2, 2. And what you should be able to do is, number one, find a normal vector to the surface at that point. That's an n. And then find the equation of the tangent plane to this surface at that point. Go ahead, why don't you guys do it? And then we'll do it. All right.
You want me to do it?
You got some confidence in what you did?
Yeah, guess so.
You guess so? All right, we'll give people another minute or two if you want. That'd be great. Anybody? Confident answer? Go on up and do it. All right, who wants more time? Well, let me ask you that. You want more time? Oh, you want to come up and do it?
I think I might. I got a quick.
Go ahead.
Normal, is that just a gradient of f over the mag? How you get the normal again? And there'll be the unit.
You get the normal by changing this surface into a level surface to a fourth dimensional object W.
Okay, yeah.
Yeah, and you got the normal? You don't have to make a unit normal out of it. You don't have to divide by the magnitude. Just get the normal. And once you get that normal, then you use it to find the equation of the tangent plane.
No, I got it now.
You got it?
Yeah.
Okay.
What's that?
I think I don't want to go up and do it though.
I think I have the wrong answer. I'm not.
Can you just subtract z?
Yes.
Okay.
Set it equal to 0. Subtract it. Set it equal to 0.
Oh, those switch for a second.
I don't know if I'm using the right
Those are
notation.
gradients. Those are good. Those are good. Those are good.
Yeah.
I don't know.
He's got sixes. His sixes are the partial derivative.
Yeah.
Yeah, it's like
Really
that.
not going
For
wrong
a
way.
second, I'm like,
But
okay,
that's
those
all
are
right.
partials.
We know what he means. We know what he means. You're all set, Liam.
Yeah, you got this, man.
You got this. You got this.
Yeah, you got it.
I'm confused. We plugged in the 2 in the middle. and
Equals 0.
like, why is it 2, 1?
Nice. All right, and that 7 at the very end is a 0. All right, that's good. That's good. No, that was fine. That's fine.
All right. So you set W, and technically what you do is set W equals 0, subtract the z, just what he did. You find the partial of x, which is y, partial of y, which is x, partial of z, which is -1, okay? And then you want to, so this is the gradient to W, okay? And that gradient to W is going to be a vector normal to its level surface, our surface, okay? And that's the y, the x, and the -1 at the point 1, 2, 2. At the point 1, 2, 2, the y is going to be, here it is, 1, 2, 2, just what he said. Y is 2, the x is 1, this is a -1. That is our normal vector to the surface at this point. The tangent plane, therefore, has the equation 2 times x minus 1, point, using the point, plus 1, that's the coefficient here, y minus 2, minus 1 right here, z minus 2 equals 0. That's perfect. That's perfect. I think, hey Dan, I think on the test, I'm not sure if I have it this form.
Or simplified.
What's that?
Or simplified.
Yeah, I probably have it like this. You got -2, -4, minus 2 equals 0, or something like that, okay?
Oh man, I don't know if I can do it now.
Oh, yeah, I know. Unnecessary complications in there. Yes?
So if you want the unit normal vector, you're gonna just ask for it? Or?
Yeah, if I ask for, yeah, but I'm not. But in this context, there's no need for a unit normal vector.
Are we? So we're not gonna need a unit normal for this S?
I don't think so. I don't
Yeah,
think you
I
will.
know.
Will
I'm
you?
just
I don't
throwing
think
that
so.
out then. Bam, it's gone.
We had our list of
Trash.
topics, right? Limits,
Yeah.
partial derivatives, directional derivatives. I don't think you do,
Okay.
but you need this normal
What
because
if
of the
there's
tangent
an
plane.
E-Burns?
What's that?
What if there's an E on the test?
Oof, I know,
And
there
you're
could
not
be
there.
too, and I'm not there. You're gonna have to go with E.
I'll
That's
have
what
to-
happened to the last group of people who took the test.
I'll have
in
to
the test.
message you on Facebook, I
All
guess.
right. Liam,
For section 12 to 17, I'm just messing up my notation. The difference between a max directional derivative, direction of a max directional derivative, and a directional derivative in the unit vector direction. Like, what are the difference between?
wow, let's take a look at this. Okay, here's what we have. We've got a surface, okay, and we've got a point. We've got a point on that surface. You've got an infinite number of directional derivatives to the surface at that point, the set of which will constitute the tangent plane. Okay. Now, what's the direction of the maximum directional derivative? The direction is in the direction of the gradient.
Okay? That's the direction of the maximum directional derivative. It's in the direction of a gradient. The gradient is a two-dimensional vector, a vector in the xy plane, pointing in the direction of maximum change. Okay? That's what that maximum, that's the direction of the maximum directional derivative. What is the maximum directional derivative? It's the slope of that tangent line in that direction. What is it equal to? It's equal to the magnitude of the gradient. Okay? So the gradient's pointing in the direction of the maximum directional derivative. The actual maximum directional derivative is the magnitude of the gradient. Now you also had a unit vector kind of thing, because what's given is, of all the how you find a directional derivative is use a unit vector in the direction in question. Okay? So the unit vector that's pointing in the direction of the maximum directional derivative will be the unit vector in the direction of the gradient. The gradient doesn't have to be a unit vector. It's some vector. Matter of fact, it normally wouldn't be. It's some vector. Now, if you want to find the directional derivative in any direction, you have to take a unit vector in the xy plane. So what you would do then is make that into a unit vector. Okay? But if the question is just to find the maximum directional derivative, simply take the magnitude of the gradient. That's all you have to do. Hopefully I answered your questions there.
Yeah, so the directional derivative, the directional maximum derivative is the direction of the gradient.
Yes.
And then its unit is the unit vector of the gradient.
Yeah, that's true.
And then the maximum directional derivative magnitude is the magnitude of gradient.
That is perfectly correct. All right, other questions?
So the n that we find in here is already a unit vector?
No, it may not be, but we don't need it to be. Okay, this normal vector here, which is the vector 2, 1, negative 1 here. Okay, this is our normal vector 2, 1, negative 1. It's not a unit vector, but we don't need it to be a unit vector. All we need is some vector that's normal to the curve. Okay, and it doesn't have to be a unit vector.
So in the case of we find the unit vector for that normal vector, what would that be used for? Or what could we use that for?
Well, it would be used for tangential normal components. No, even those. No.
Is it just for like that Webasine problem?
Yeah, that's just about right. You know, that's the only time you're going to need that. Those unit ones, yeah.
Okay.
Because even tangential normal components of acceleration, a dot and a dot t. Wait. Hold on. Yeah. In that case, you do need unit normals and unit tangents, because that's the amount of acceleration along the unit normal and along unit tangent. For that particular problem, you would need it. But that's it, though.
For what problem?
The problem of finding normal and tangential components of acceleration.
Do we have to do that?
No, that was last chapter.
No. Yeah.
Don't forget it. Yeah, I agree.
Throwing it all out then.
Yeah. Yes.
Can we do a problem where we find these three, the gradient, mass, differential, and this thing?
Oh, that's what Liam was just talking
Yeah, can
about.
we like, get an example of that?
Yeah, let's do one. Okay, here we go. Let's do this one right here. We got a problem right here. Here's the question. Question is, we got a surface, we got a point. Let's do the question that Liam was asking, and let's do these things. Okay, first of all, we know the gradient already. The gradient is actually the gradient. This is the gradient of W. We want the gradient of Z here. Okay, let's find the gradient of Z. It's the partial with respect to X, the partial with respect to Y. It's equal to partial with respect to X is the Y, partial with respect to Y is the X. And you'll notice it's the first two components of the gradient for the fourth dimensional thing. Okay, so that's the gradient of Z. The gradient of Z at the point in question is 2, 1. Okay. Now, here's our surface. Our surface starts at the origin and moves up this way. It's the product of x and y. It's going up. We've got the point 1, 2. Let's say 1, 2, 2. It's a point on the surface. surface is coming up like this. Okay? We've got a gradient down there of 2, 1, okay, in the xy plane. That's pointing in the direction of maximum change. It's pointing in the direction of that maximum directional derivative, okay? Now, what is that maximum directional derivative? Yes, it's exactly what it is. The maximum directional derivative, okay, is equal to the magnitude of the gradient, which is equal to the square root of 5. Okay? 2 squared plus 1 squared, square root of that. That's the steepest of all the tangent lines we have at that point of that surface. The square root of 5 is the steepest. Okay? What's the direction? It's in the direction of the gradient.
Square root of 5 is a slope, right?
It's the slope of that line. That's exactly what it is.
Just at that point, though.
At that point. At that point, it is. It could be different at other points. Yes. Now, here's what we're going to do to verify this. What I'm going to do is find the directional derivative of our surface, z equals xy, at this point in this direction. Let's take a unit vector in the direction of the gradient. The unit vector in the direction of the gradient is 2 over the square root of 5, 1 over the square root of 5. What I've done is divided the gradient by its magnitude. Now I have a unit vector down there along the gradient, pointing in the direction of the gradient. And what I'm going to do is find the directional derivative of our surface at that point in this direction. I'm going to find a directional derivative. What should the answer be to that question of what is the directional derivative, okay, to our surface at that point in this direction?
Same thing.
Which is?
The gradient.
Not the gradient.
Oh, sorry.
I want to find the directional derivative in this direction.
Oh, it'd be the max directional.
Yes, and it's going to be equal to what? What's the answer? Square root of 5. Okay, we should find that the directional derivative in this direction is that square root of 5. Okay? Let's do it. Okay? The directional derivative of our function at this point, some given point, is equal to the dot product with the unit vector of the gradient with the unit vector. So that's equal to the gradient of this function is 2, 1. The unit vector is 2 over the square root of 5, 1 over the square root of 5. Which, by the way, this 2 over the square root of 5 is the cosine of the angle that this vector makes with the x-axis. And this is the sine of that angle. Okay, it's cosine theta, sine theta. Okay, and when we do this dot product, to find the directional derivative in this direction, we get 4 over the square root of 5 plus 1 over the square root of 5, which is 5 over the square root of 5. We're close. All right, I got it. Which is equal to square root of 5, which is what had to happen. Okay, the slope of that tangent line at that point in that direction is the square root of 5. No other slope, no other tangent line has a slope that's equal to this or greater than this. This is the maximum. Okay. Now, what direction would be the minimum slope of all the directional derivatives? What would the direction be to give us a minimum? The opposite, exactly right. Head back in that direction, which would point you down the surface. It would be the opposite of this direction of the gradient, okay? Just multiply by -1, -2, -1, okay? All right, these are good. These are good questions. These are good. What else we got? Yeah?
Can you give us like another general max-min problem?
A max-min problem. All right, let's do it. And again, on the max-min problem, what I'm going to ask you is your procedure for finding a max-min as opposed to actually solving a max-min, okay? All right. But you should all, let's do one. Okay, let's see. Find x, y, and z
such that x plus y plus z is equal to, I don't know, 10, and what is true? This product of what is a maximum? Okay. All right, well, go ahead. Bless you. Is a maximum. X, Y, and Z are greater than or equal to 0.
Ernest,
Yes.
question.
Oh, you got it? Oh,
No,
good.
right, the one right before the last two, how'd you get 5 square root of 5?
5.
Yeah, it's just square root of 5, how'd you get?
Oh, rationalize the denominator. Multiply numerator and denominator square root of 5. Yep.
Yeah, but wouldn't that give you 5 on the bottom?
And then the 5's
Oh, I just can't. Makes sense.
Yeah, anytime you take a number divided by its square root, it is the square root. Okay, go ahead. Why don't you do this one out? You can do this one out. That Math 170, Programming in Mathematica, is out there. It's on the schedule of classes. Yep.
Was it not there last night?
I don't know if it was there last night, but I saw it this morning. It's on the schedule of classes, so you should be able to sign up for it. Don't all just rush right now to sign up for it. 2 weeks in January. Monday, Wednesday, Friday, hour and a half each time. I mean, if you're not doing much in January, then consider it. What are you doing in January, Homer? What, snowball fights or something? Oh, you working?
Yeah. Yeah, I'm working. I don't know if I can make it.
Oh, man.
It's in the morning though, right?
Yeah, it's like 9 to 11:30. Monday, Wednesday, Friday. Yeah. Yeah.
Wait, we're actually going to have one of these problems and that's all we have to do?
All you have to do in the test is explain how you would solve it if you were trying to solve it. You don't have to actually solve it.
I don't know that.
It is a multiple choice exam.
That sounds like an open response question.
No, it's not. It's easy enough to make it into a multiple choice question. First step.
You say so.
First step is here's what I do. Okay, here's the problem. What's your first step? Your first step is to express the quantity P in terms of how many variables? 2. So that's A. Express the quantity, express the variable in terms of 2 variables. B. First step. Cut down an oak tree. C. Go birding at Arcadia, which is what I did this weekend. D. Climb Mount Everest. So E. None of these.
Is that what you did 2 weekends ago?
What, 2 weekends ago? I didn't go to Arcadia.
Climb down Everest.
Climb down. Yeah, right.
Isn't Arcadia in Maine, right?
Okay, I don't know if it's the Arcadia is in East Hampton. The Acadia or Arcadia, I don't know, but there's a big
national park in Maine,
In
which
Maine,
is,
okay.
yeah, in
I
Maine.
thought that was Arcadia.
Yeah, it could be Arcadia as well. It could be.
Definitely starts with an A.
Yeah, I do know
for
that.
Sure, without doubt.
That's true. We've been there. We've been there. Matter of fact, I think I have a picture in back of my desk in my office here of Gene and our two kiddos on top of the mountain in that national park in Maine. Good stuff.
If only you had a picture of the sign, then we could
I
know
know,
which one
I
it
know.
was.
That's true. I took some pictures this weekend, though, of cedar waxwings that are just stunning. These are stunning. I think I'm going to quit this job, and I'm going to go into production and sell a set of 4 of my cedar waxwing pictures just from this weekend. You know, to what? To offices, businesses, dentists, doctors. They can buy a set of 4 of my and put them in their office. You know.
I know a dentist, Burns.
You do?
I do.
Wow.
Ah.
Wow. It doesn't look it though, Teddy. But anyhow. Sorry. I'm sorry. I'm sorry. Sorry.
I'll show it down this big. Got Burns.
Oh man, I'm sorry. I couldn't
That's
help
crazy.
it.
Don't do that, bro.
What's that?
That's crazy. Don't do that.
Yeah.
That sounds fun.
No. Oh really? This is too difficult, huh? To do that? To sell this? Yeah. I don't know how.
I just don't feel like it's.
You could do those engravings. You could like carve them into brass and then.
Yeah, there's a lot of possibilities.
Endless.
The problem is to get it out there. You know what I mean? To actually have people aware of what you're doing, and that would be a difficult task. I'd have to advertise on Google or Facebook or do something like that.
You can use your fame that you gained in the mathematical world.
Yeah, but you know what? That fame is it's rather limited, though. You know what I mean?
I mean, like almost killing that guy must have given you something.
Yeah, that's true too.
You're
That's
saving another
true.
guy's life.
Yeah, that's true. I got a little bit more there. That's true. Now,
Maybe input.
oh gosh,
Did you actually write the steps
How
out?
many worked out for Justin?
what's that?
Did you actually write the steps out?
No, what you have to do is the first question is, like I said, get it in terms of 2 variables, you know. The second step is to find the critical values by setting the partial derivatives equal to 0. And then, so you should know that. And then you should know how to determine the second partial test. All right, how to find D. All right. Do I ask you to find D? I'm not sure if I ask you to actually find D or know that D has to be greater than 0. In order to do a maximum, you have to know that D is greater than 0 and second partial with respect to x, okay, is going to be, what's that?
Less than or than.
Yeah, the second partial with respect to x is going to have to be greater than 0 or less than 0 for a maximum. Less than 0. Yeah, that's what you were saying, huh? Okay, yes. Less than 0. Because that, yes. You think this way. Second partial with respect to x, negative, concave down to get a max. Dylan,
Can I see a proof theorem for D?
can you see a what?
Proof theorem for D.
For D? Yeah, no. You can't. Wow, you know what? I'd have to think about that because.
You don't even
You guys
show
want to see
up.
that? I know.
I don't know about that proof.
Club pretender.
Make that
Yeah.
much.
Today we're doing the problem. Today's the last meeting we're going to have for a while until January.
Wow.
So last pizza for a while.
Wait, do we like fire back up again in January? Do we
Yeah.
take another test?
Yeah, there's another test in March. So, and the winner of the $100 it's the sum of the 2 tests.
Danner.
Wait, so does that mean you guys get like $75 then or something?
No. If they're tied, you mean?
Yeah.
still in first?
Do they get the
I don't know. That's a good question, Liam. I don't know if we're still in
Don't
first.
check. Let's just.
I know that. I don't want to check.
I've been telling everyone we're in first place.
I know. I don't want to check. I think we won't check ever for the rest of the semester. Yes. Yeah. Here you go. All right, you guys ready? Let's do this.
You can just say we can get a big sign that says we were number one because at some point we were.
We were. We absolutely were. And as far as I know, at this moment, we still are. I don't know.
I still tell people.
All right, let's do it. Find x, y, and z such that the sum is equal to 10. And all right, step 1. We need this in terms of 2 variables. So solve for z, use your constraint, multiply it out. Okay. Find critical values. Okay. Take the partial of p with respect to x. And set it equal to 0. And let me factor out a y cubed while I'm here. Take the partial of p with respect to y. Set that equal to 0. Factor out an xy squared. Okay. Now, what you want to do is take arrangements of the factors here to set them equal to 0. The bottom line is, however, if y is 0, x is 0, there's a critical value, but it's certainly not a solution. If y is 0 and x is 10, there's a critical value, but it's not a solution. As soon as you have any one of these equal to 0, we don't have a solution to maximizing that product. The product would be 0. So forget about those combinations with these factors on the outside here. The only ones that matter are these two, this one and this one here. So let's set those equal to 0. Bless you. And I think what I would do is multiply the top by -4. And add them up to get -10 plus 5x equals 0. The y's would cancel. 5x equals 10. X is 2. X is 2. Then y is equal to 6. And if y is 6, z, being 10 minus x minus y, is equal to 2 as well. Okay. That maximum product is x2, 6 cubed, okay, 216 times 2. It's 4 times 216. That's 864. That would be the maximum product that you could get out of those 3 numbers whose sum is 10. To prove that it's a maximum, though, you would find d. You find d by taking the partial of our function here, okay, with respect to x. Take a second partial with respect to x, second partial with respect to y.
It's the second derivative test, right?
Yes, this is the second derivative test. It's called the second partial derivative test. And take the mixed partial, either xy or yx, it doesn't matter. Oh, okay, and square that one. That's d. And what you would do is find d. Now this is where it gets a little messy here. Second partial of p with respect to x is a -2y cubed. That one's not bad. Okay. Times second partial of p with respect to y. This one is kind of bad. This would be 60xy minus 6x squared y minus 12xy squared minus the mixed partial squared. If I do x and then y, here's x, and then do that with respect to y, so you get 30y squared minus 6xy squared minus 4y cubed, and square that. And what you would do, I'm not going to do it out, but you would substitute in the point in question. Our point in question is the 2, 6, 2. So you would substitute in, where x is 2 and y is 6. And what would happen is you'd get d greater than 0. Okay? You would get d greater than 0. And in addition to that, you would find that the second partial with respect to x is going to be less than 0. Now, could we do that one at least? Second partial, yeah. The second partial with respect to x is a negative 2y cubed. Y is 6. So you get that less than 0. So that, we can verify that one. The other one's just too messy. But you don't even have to do it out on the test. You just merely have to know that how do you get a maximum value where d is greater than 0, second partial with respect to x less than 0. Okay?
Wait, so how much do we need to know?
Not a heck of a lot. You have to know to set the variable to set the function to 2 variables. Find the critical values by setting each of the partials equal to 0, and knowing that to find a maximum, d is greater than 0, and second partial with respect to x is less than 0, or the other way around. Minimum, d would have to be greater than 0. Second partial with respect to x would have to be also greater than 0. Liam?
So we're not even going to be solving it, we're just going to be...
No, you're just going to explain how you would solve
you just
it.
set each partial equal to 0, and then you just need to know if the second partial is greater than or less than 0.
You have to know if this d is greater than 0 first, and second partial with respect to x is less than 0. That will give you a relative max. Second partial with respect to x greater than 0 gives you a relative min. And you should realize, although it's not going to come into play, but if d is less than 0, you have a saddle point. Okay, a saddle point. And if d equals 0, the test fails in general, and that's kind of a nightmare. You have to look at the function and see what's happening, because this test could fail. Okay, how are we doing?
I'm confused on where that 40 plus 8 came from down there at the...
This multiplied by negative 4. I multiplied by negative 4 because I wanted opposites on the y, so they would cancel out.
I see.
Okay. All right, we get the math team meeting in about 15 minutes, 13 minutes. We should have pizza coming in. Test, you may take the test. It's in the test center anytime now or tomorrow at any point. Okay? See you Wednesday. Or see math team shortly.
Forward.